Hey gang, welcome back. We're going to finish up the 7.2 lecture. I'm starting from slide 12 in the 7.2 slides that were given in the during the last lecture. So we're going to continue on with these examples and finish out this section for the most part, except for the recommended homework solutions, which will be in the next video. So last time we talked about the normal distribution and learned how, theoretically we find probabilities and quantiles using the notation that the book uses, and also the chi-squared distribution for z sub I squared. Today we pick up with the chi-squared a little bit more, but the chi-squared distribution does really play an important role in many inferential procedures, even beyond just the chi-square distribution. For example, suppose that we wish to make an inference about the population variance sigma squared. We do something in analysis. Sometimes we do a chi-square test, and chi-square tests are usually used to determine whether a population variance is equal to or less than or greater than some a value based on a sample, y sub 1 through y sub n, which comes from a normal population. So chi-square distribution being related to the normal distribution requires that our samples still come from a somewhat normal distribution. Okay. We'll also show in chapter 8 a good estimator for sigma squared is the sample variance, which is s squared, which equals 1 over n minus 1 times the sum of I equals 1 to n of y sub I minus y bar squared. All right, because oftentimes we don't actually know the value of sigma squared or the population variance, and so oftentimes we'll use things like s squared in place of it. So a good this chi-square distribution we're about to talk about here is the one that we see most often in practice, that pops up most often. So if you did a chi-square goodness of fit test with me in biostat or with Dr. Trimboli at some point, then most likely the chi-square distribution you were using was related to this one here. Okay. So theorem 7.3 kind of defines it out for us, and it says let y sub 1 through y sub n be a random sample from a normal distribution. Again, important that it's normal, with mean mu and variance sigma squared. Then technically the test statistic here is n minus 1 times s squared over sigma squared is actually equivalent to 1 over sigma squared times the sum of y sub I minus y bar squared. And this particular we're really concentrating on this piece here more so than the other one with the left hand side of the equation, but it has the s squared random variable here has a chi-square distribution with n minus 1 degrees of freedom. So the degrees of freedom have changed a little bit, and that's what we're usually used to, is n minus 1 degrees of freedom. But it should also be noted that y bar and s squared are both independent random variables. Okay. And that makes sense because the y sub I variables have to be independent to begin with. So anything we create using them, any statistic we create using them will become independent, will be a random variable, but then y bar is independent of s squared in this scenario. Okay. So we're going to just jump into an example here because we've already kind of looked at the chi-square distribution a little bit. But example 5 from the textbook in this section says, in example 2, the ounces of fill from the bottling machine are assumed to have a normal distribution with sigma squared equal to 1. Suppose that we plan to select a random sample of 10 bottles and measure the amount of fill in each bottle. If these 10 observations are used to calculate s squared, it might be useful to specify an interval of values that will include s squared with a high probability. Find numbers b sub 1 and b sub 2 such that probability of b sub 1 less than or equal to s squared less than or equal to b sub 2 is equal to 0.9, or 90% if you want to think about it that way. So this isn't a terrible problem here. So we know the following facts. We know that sigma squared, based on what was given to us, is 1. All right. We also know that they're doing 10 observations, so that's our n, our sample size. So we know n equals 10. And since we're dealing with a s squared, a chi-square distribution based off s squared, the degrees of freedom here equals 10 minus 1, which just equals 9. So we'll need that for any finding these values that are these b sub 1 and b sub 2 values we're missing. So we're asked to find the probability that b sub 1 probably that b sub 1 is less than or equal to s squared, which is in return less than or equal to b sub 2, some value that. And if we kind of use the same scenario or the same kind of rationale behind what we did when we were doing this with the normal distribution, that function I boxed in here on the first slide, n minus 1 s squared over sigma squared, is what we kind of have to do to turn this into a chi-square distribution. So we need to make that s squared in the middle look like that, and in turn, by doing that, we alter b1 and b sub 1 and b sub 2. So this should equal the probability of n minus 1 times b sub 1 over sigma squared, which is less than or equal to n minus 1 s squared over sigma squared, which is less than or equal to n minus 1 times b sub 2 over sigma squared. All right. But we know that sigma squared equals 1, and we know the degrees of freedom n minus 1 is equal to 9. So this cleans up actually kind of nicely to be just the probability that of 9 times b1 is less than or equal to sigma squared is 1. We could actually just make that go away in the middle, but that's technically a chi-squared distribution we're dealing with, so we can call this chi-squared for now. All right, it's less than or equal to 9 times b sub 2. All right. Something that I didn't note earlier, our last section that I probably should have, is the domain of the chi-square distribution. If you look back at the graph way back here, notice it starts at 0, so there are no negative values and no negative quantiles across the u-axis here for the chi-square distribution. All those values are positive, so it's not symmetric either. So we have to find both of these things accordingly. So b1 and b2 will be very different from one another in this case. Okay, and this has to equal to 0.90 or just 0.9. Okay. So if we think about that image, we've kind of got this thing going on, right? It's kind of a long tail on the right skew distribution, and we're looking for values here and here roughly, just ballparking it. We'll call them a sub 1 and a sub 2. You can call them x1, x2, whatever you want, just some different variable to make them different than 9b1, 9b2. In the area underneath the curve between those 2 points is supposed to be 0.9. So that means we've got 10% left over, so the area in this tail down here is 0.05, and the area in this little smidge here is also 0.05. So the area under the curve is still 1 in this case. Okay, to be a valid probability distribution, that always has to be the case. So define a sub 1 such that the area between is 0.9. We need to use the q chi-square function, and we can do q chi-square of 0.05 on the bottom side, this area down here, comma, then we have to insert the degrees of freedom of 9. All right, we'll get that answer here in just a minute. Then a sub 2 is equal to q chi-square of 0.95, area below a sub 2, 0.9 plus 0.05, 0.95 and 9, and that'll give us that upper bound of this particular function. So we can also use the table. Obviously, we've got 9 degrees of freedom, and we're interested in finding the I guess the alpha equals 0.05, so let's look at it and see if we can find the values before we use the calculator. So since the area above, and I believe, if I'm not mistaken, yes, the area above here, so if we want to find that upper bound using the chart, we have to use the value of 0.05 to find the upper bound, so it's opposite of how you would do it in the calculator. So if we come to the 0.05 and then go down to 9 degrees of freedom, it's not really showing me what I want there. I don't think yeah it is. Sorry, that's the correct number. 16.919. So that's what R should give us as well. To find that lower bound though, we have to look at this and not do 0.05. But if the area alpha is the area to the right, then we have to look at the 0.95, which is on the previous page. So 9 degrees and 0.995 should be 3.32511 roughly. Okay. So we could probably round those to about 3 decimal places and be comfortable with that. But in R real fast, let's do those again. Clear out the stuff I had from last time, and I'm doing q chi square of 0.05 comma 9, and it does indeed give me 3.325. Notice again I plugged in 0.05 because this function finds the values less than or equal to the area we're plugging in, or finds that value that represents the area to the left. So that's a sub 1, and then a sub 2 to make 90% is going to be q chi squared of 0.95. Should be 0.95 of 9, and that should give us the 16.91, and it does round up to 9. Again, this is more accurate than the table, but you know, nonetheless, it's they're both fair game to use in these problems. Okay, so we've got those two values, but we're not done yet, unfortunately. So I'm going to round them to 3 decimal places. 3.325 was A1, and the upper bound was 16.919. The numbers we actually need here to represent s squared, and I guess technically the way the book did this was they just divided by 1 and had n minus 1 times s squared here. That's acceptable as well. But technically we're using the chi-square distribution, but this is really a bound on s squared, so we're really looking for the numbers b1 and b2 that makes this true. Okay, so setting each 9b1 equal to the a1 value of 3.325, the lower bound, and solving that, and then 9b sub 2 equal to 16.919, and solving for b sub 2 here, we should get that b sub 1 equals 0.369 and b sub 2 equals 1.880. Okay, thus an interval that includes s squared with probability of 0.9 with a probability of 0.9 is 0.369 to 1.880, or just 1.88 if you want to, and that's pretty much all there is to that. So not too bad, right? Again, I wish the calculator had all these functions in it to find some of these things, but for chi-squared in the F distribution you can't find the quantiles using the TI calculator. So the table, like I showed you, or R are your best friends in this case. Okay. Alright, so that's the chi-square distribution in a nutshell. We could also find probabilities under that, and I would ask you to do that, but if I did that I would have to give you more information. Like, you would have to know what s squared was for each endpoint here, in sigma squared and n minus 1, and then you could get these bounds, and then I could ask you the probability. So that's fair game as well for problems like this. We're just not going to do an example of that today. We're moving on to the t distribution, and the t distribution is one of my favorite distributions of all of them. I guess if you could have a favorite one, the t would be mine. The reason why that is because the t is more useful in applications across statistics, because it has a lot of properties that allow it to when a data set's not 100% normal, but it's close enough, the t-distribution can kind of give you some wiggle room to do the same thing that you would do with a z-distribution or a standard normal distribution. So in a way, the t-distribution is very similar to, or the t-distribution is very similar to z, and there's a reason for that, obviously, because if we let z be a standard normal random variable, and we've seen that before, and let w be a chi-square distributed variable with n-1 degrees of freedom. So the w here represents the chi-squared, and it's divided by its degrees of freedom. Okay. Then it said that that function, or that statistic, is said to have a t-distribution with n-1 degrees of freedom. Okay. Now that's not the way you usually see the t formula written. It usually looks a lot like the normal distribution's standardization formula for z. So if we do a little work and replacement here, t equals that z over square root of w divided by n-1, right? In the top, we know z is equal to y bar minus mu over sigma divided by the square root of n. And in the bottom, underneath that square root, w is a chi-squared distributed variable, n-1 degrees of freedom, so it matches the one we just learned about, the s squared. So that if you recall from that slide earlier, that's n-1 times s squared divided by sigma squared, and that's all divided by n-1. So some things are going to cancel out and clean up for us rather nicely. Specifically, the n-1s are going to cancel, right? And we end up getting y bar minus mu over sigma divided by the square root of n, all that divided by s divided by sigma. Well, the sigmas are going to cancel out, and we end up getting this. This is what it should look like: y bar minus mu over s divided by the square root of n. And that, folks, is the way that it should look. And recall, the only difference between that and the z random variable that standardized values to fit on a standard normal curve is that z equaled y bar minus mu over sigma divided by the square root of n. And so when we don't know the population standard deviation, sigma, we can replace it with s, and that therefore the t kind of becomes handy. Another thing I want to go mention about the t, and you may have heard me mention this before if you've had me in another class, but the t distribution came about for small samples originally, samples that were smaller than 30. And a man named William Seeley Gossett invented it, or came up with this idea, because he was doing work at the Guinness Brewing Company, and only so many batches of beer you could produce at one time, and this was in the I think late 1800s, early 1900s, sometime around that period, really a while back. And so they didn't have like warehouses of vats of stuff, so they could only produce so many vats of beer at a time. But because they had small samples to perfect the beer, he needed a way to do some statistical stuff, and since he was a chemist and a mathematician and probably a couple other things, he came up with this, and it's called the student's t-distribution because of him. All right, so just a cool little story that I like to tell when we talk about the t-distribution. All right, so how does the t-distribution and the standard normal distribution actually relate to one another? Well, here's kind of an example of that. The red line there is the t-distribution. This is the t, and the blue line up here is the z, or the standard normal distribution. This is actually, we'll just call it normal 0, 1 here for the standard normal distribution. And this is actually a t with 2 degrees of freedom. Okay. So what we're looking at here is notice that the t-distribution has what we call fat tails. In other words, the tails are higher up for the t-distribution than they are for the standard normal. That's important to note because that changes how the probabilities underneath the curves come out for us. So notice in the shaded in red here, I've got the area for the under the t-distribution, and it comes out to a wider spot here, so that probability is very similar. They both contain a lot of the same area, right? Except for this little area here is in the t, and that's a lot less area than what's all up here that's not shaded, double shaded in blue. And so there's more probability between these 2 points here and here for the normal distribution, or the standard normal distribution, than there is for the t-distribution. And there's a reason for that. What we say when we see fat tails on a normal looking curve like this, or for the t-distribution, is we say that there's more variability. So the fatter or taller your tails are, and the lower down your mode is, so to speak, your high point, the more variability there is in that thing. So the variance would be larger in this case. It varies more wildly. Both the probabilities will be very different and less, and also the values along the axes here might be a little bit different as well. All right, so they won't always match up. They're not going to be exactly the same as the normal distribution for the quantiles. Because of that, another thing I want to note is, as the n value, the sample size, see if I can get this to right here, as n approaches infinity, so the bigger n gets, and that means the degrees of freedom get larger, right? The closer the t-distribution gets to the z-distribution, or the normal standard normal. That's important. So for example, say you had a you knew the population standard deviation, so you're rocking out the standard normal distribution, and say that sample size was, say, like 100. If you then went and took a lot less samples, say like 5 samples, and you went with the t-distribution, your probabilities are going to vary very differently, and your quantiles will vary differently from what the normal distribution is. But if we increase that t-distribution up to 100, it gets closer, like the curve becomes closer to the curve of the normal distribution. The tails become narrower, and so the bigger we make n, the closer to the normal distribution we get. The normal distribution is where it's at. It doesn't change based on the sample size. Okay, so it is what it is. But the t-distribution does. And so closer to infinity, as we get bigger and bigger, the closer to a standard normal we get. And so when you take really large samples, it doesn't really matter whether you do a z interval or a z distribution. Use the z distribution versus the t distribution. Okay. I'm going on. So the thing about I wanted to note here, and that you probably should write down somewhere, is that note fat tails on the t means we have more variation than in the z curve. So basically just saying that the t has more variability than the z. All right, so that changes a lot of things around. Some useful functions before we do an example of this problem with one of these. You do have an inverse t and a tcdf function on your calculator, so you can find these values on the TI calculator. In R, the R functions in R are going to be, you've got PT for the probability, to find probabilities, and the inputs on the quantile, or the value you're looking for, to be less than or equal to, and then the degrees of freedom, which is n-1, and that of course finds probability that y bar in this case is less than or equal to y, or y bar, really it works with both. Q, because if we're doing sample means, it's one thing. If we're doing just a single value from a data set, it's kind of the same principle. And then you got QT for the quantile function for t, and that just takes the probability and the degrees of freedom. And of course it finds the probability that y bar y is less than or equal to phi sub p equals p, and again it's finding the quantile phi sub p, which I guess here we could call t sub alpha, because that's really what a t-score is referred to as in a lot of texts. Okay, so let's do an example using the t-distribution. So the tensile strength for a type of wire is normally distributed with a known mean mu and unknown variance sigma squared. Unknown variance sigma squared. That's a key to telling you I probably need to use the t-distribution. 6 pieces of wire were randomly selected from a large roll. Y sub I, the tensile strength for portion I, is measured for I 1 through 6. So 6 different samples. The population mean mu and variance sigma squared can be estimated by y bar and s squared, respectively. Because sigma squared sub y bar equals sigma squared over n, it follows that sigma squared sub y bar can be estimated using s squared over n, or just s over the square root of n, as we've seen already. Find the approximate probability that y bar will be within 2 times s, 2 times the standard deviation, over the square root of n of the true population mean mu. This one actually cleans up rather nicely. So we don't know the mean, we don't know we do know a little bit about the sample size, I guess, but it doesn't really matter what the sample size is here, so to speak. We've got what the setup here would be based off of what they told us. Let me do that in blue instead of red. Is the probability of negative 2 times s over the square root of n is less than or equal to y bar minus mu. All right, that's that within clause, and less than or equal to 2 times s over the square root of n. All right. This one's going to just equal, if we divide everything by s over the square root of n, we get the following. We get negative 2s over the square root of n times square root of n over s is less than or equal to y bar minus mu over sigma divided by the square root of n, which is less than or equal to 2s over the square root of n times square root of n over s. So I just did the reciprocal there, which ends up equaling just the probability of that t falls between -2 and +2. So that one kind of cleaned up rather nicely, okay? Now the degrees of freedom will be important here. We didn't have to plug them into our formula here and divide anything by them because they were going to cancel out anyway. So that wasn't important in this case. But this is a t-distribution. With n-1, and recall n equaled 6 originally. n-1 equals 5 degrees of freedom. Okay. So if you use the table for the t-distribution, which we haven't looked at yet, it's a little different than the normal distribution table. So I'm going to put the rule down here, and then we'll look at the table. So using the table, I don't remember what number it is, but we'll look it up in a second. using table, go to degrees of freedom row 5, then look for value closest to 2. You're not always going to find the values you want, and so this ends up being the value as we'll see in the table in a minute, 2.015 in the t sub 0.05 column. I don't, and we'll get this in a minute. I'll finish that statement out in just a second. Let's look at the table first before we go on. So on the t-distribution table, which is table 5, it's just a small table. We know our degrees of freedom are 5. So I'll come down to the 5th column and I just kind of keep going until I see something closest to 2 as possible, and that's the 2.015, and that's going with alpha equals 0.05. That knowing that alpha equals 0.05, the area above tells me exactly tells me the approximate probability here. It doesn't give me the exact probability. And so if we use that value, and again, the t-distribution, just like the z-distribution, is symmetric, so, and it's centered at 0, so we've got, if we find the positive value on the upper end like we just did, it's the same value but negative on the bottom. So this is equivalent to probability negative 2.015 is less than or equal to t is less than or equal to 2.015. But as I said, those two values cut off a middle region, and this upper region here was for the alpha equals 0.05, which means down here is also 0.05. So we know that this has got to be 0.9. That's an acceptable answer here, but I think we can be more accurate than that using either your TI calculator or R. If you use the TI calculator, the answer you should get will be a lot more. So on the TI, we can use the TCDF function, so the probability that we're between -2 less than or equal to t less than or equal to 2 is going to be equal to TCDF of -2, 2, 5. So that's from -2 to 2 and degrees of freedom 5. And when you do that, I'm not going to do it for you, but it's going to be 0.8981. So it's close to 0.9, but this is more accurate to be around 89.8%. And you're going to get a similar answer with R, but with R, again, you're going to use the PT function for probability, and you do PT of the upper bound value of 2. And then you got to put in the degrees of freedom. Unlike the normal distribution, you just put in the degrees of freedom of 5 minus PT of -2, 5, which then equals 0.8981 as well. So either way you do that, this is a more accurate answer, and I would probably rather see this over this. I don't like approximations when we can be a little bit more accurate. I mean, we're still approximating technically because we're rounding off, but to round it all the way to 0.9 is when it's not exactly that is a little untruthful, I guess. That's the word I'm looking for. So that's the t-distribution in a nutshell. We found a probability, but we could also have to find the quantiles if we needed to, and you may have to do that in a problem in the homework at some point. All right. The last distribution we're going to discuss is called the F distribution. And if you've taken a applied stats class, the F distribution comes into play when we want to analyze multiple means across groups in something we call an ANOVA. So this test statistic that we get from there is called an F statistic, and it comes from the F distribution. Which what it's really doing is not testing the means, it's testing the variations of the variances between groups, and the F distribution does exactly that. So if we let W sub 1 and W sub 2 be independent chi-square distributed random variables with n sub 1 minus 1 and n sub 2 minus 1 degrees of freedom respectively. So both of these are chi-square distributions. So we're taking a chi-square. Remember, that's checking out s squared, our way to approximate s squared stuff. And then W2 is another one that's doing the same thing. We're basically doing a ratio of the variances compared to one another, all right? And so that's what this formula technically does. But that formula is said to have an F distribution with n sub 1 minus 1 numerator degrees of freedom. So you'll see that term used a lot. Sometimes I just call them NDF for short, and then DDF for the denominator degrees of freedom, which is n sub 2 minus 1. Okay. Again, this can be rewritten as well. And the more common way you see this written is not the way that the definition writes it. But if we've got W sub 1 divided by n sub 1 minus 1 over W sub 2 divided by n sub 2 minus 2, or minus 1, sorry. Got 2's on the brain there. The upper part, the W sub 1 part, is just a s squared or chi-squared version of that s squared chi-squared formula we saw earlier. So W1 becomes n sub 1 minus 1 times s sub 1 squared divided by sigma sub 1 squared. And that whole thing there is divided by still n sub 1 minus 1. And then we divide this whole thing by n sub 2 minus 1 times s sub 2 squared of a second sample. That's the other thing to note. These S1 and S sub 2 are coming from different samples, usually. Divided by sigma sub 2 squared divided by n sub 2 minus 1. You clean all that up, and what you end up getting is s sub 1 squared over sigma sub 1 squared, all divided by s sub 2 squared divided by sigma sub 1 squared. Okay, and sometimes you'll see it written, and this is probably an important thing because it'll come up in one of the homework questions, whether one I do or one I assign you. But you can think about this as s sub 1 squared over s sub 2 squared, which we'll see it written that way more often, times sigma sub 1 squared over, oh, that's supposed to be 2 down here, my bad. Yeah, sigma sub 2 squared, sorry. Sigma sub 2 squared over sigma sub 1 squared. That's what that should be. Yep, flip. Sigma 2 goes on top, sigma 1 goes on the bottom. So sometimes you'll see it written like that too. But this is usually the most, usually see this written by itself. And then this here is the ratio of the population variances if you know them. Oftentimes we sometimes assume those are equivalent to each other and just use the sample variances in place of the sigmas. Okay. So what does the F distribution look like? It's not a lot different from the chi-square in the look. It's a little kind of more wonky looking. But again, it's the same kind of makeup. You've got alpha above the F sub alpha, and then down here would be your 1 minus alpha portion. And it's used to compare the variances of two normal populations based on information contained in independent random samples from the two populations. Your calculator does have an FCDF function, I'm pretty sure. Let me double check that real quick. I haven't used that one in a while, but I think it does. So if you go to second bars, and it's got a PDF, so I'm assuming it's going to have a CDF as well. It does. So you can find probabilities under the curve here, but you can't find quantiles with the calculator because there's no inverse F function on here. Okay. Some of you may have a different calculator than the TI. I know some of the Casios have multiple different kind of things, but we can do this in R, and that's why I'm going to do it anyway. So in R, we can use the PF function to find probabilities, and it takes into play your quantile value that you want to be less than or equal to degrees of freedom, the numerator degrees of freedom, or degrees of freedom 1 as R calls it, and the degrees of freedom 2, which is your denominator degrees of freedom. So the order in which you put these in is important because it changes the structure of the shape of the distribution and will give you different answers if you don't put them in right. So this is numerator, and this is denominator. Okay, but this gives you again the probability that y is, or y, yeah, y, we'll just call it y here, is less than or equal to q, and then qf is the quantile one, and it takes in the probability, and again df1, df2, they're the same thing here. And that again in turn is finding the same thing we've been seeing so far. Nice thing about our functions is they're all very similar, and the only difference is the inputs. And so you'll find phi sub p, or f sub alpha, if you will, when you plug this in for the value there will represent that being less than, or y being less than or equal to that value. So and that gives you p, or p you usually know. So anyway, the QF function finds this. I must be getting tired or sleepy because messing up my words here, folks. All right, so let's do an example using this. So example 7, it says if we take independent samples of size n1 equals 6 and n sub 2 equals 10 from two normal populations with equal population variances, that's an important note there that should not be ignored. That means that sigma 1 squared equals sigma 2 squared. Okay, that's an important thing to note. Then find the number b such that the probability of s sub 1 squared over s sub 2 squared is less than or equal to b. Would come out to be 0.95 for the probability. So recall from the last lecture, because I haven't mentioned this since then, this 0.95 here, recall when we see less than or equal to used, then 1 minus alpha is equal to 0.95. So that's the 1 minus alpha quantile we're about to find, or the 95th percentile we're about to find, and the alpha value that we might need if we use the table method is alpha equals 0.05. Okay, so that's important for us to note. So again, we know n sub 1 equals 6, which implies that n sub 1 minus 1 equals 5, so that's the numerator degrees of freedom, NDF. And then we know that n sub 2 equals 10, which implies that n sub 2 minus 1 equals 9 denominator degrees of freedom, DDF. Okay. All right, so if we're going to use the F distribution table to find this value of b, we don't have to do a lot. It's already set up for us. Sometimes we do have to do some extra things. If it doesn't say equal population variances and it says one population variance is twice the size of the other, then that little thing I drew out over, oh sorry, I went back one too far. This thing I drew out over here is going to become kind of important to you. Okay, so we have to keep that in consideration when we do these kind of things. So, and actually I think it's supposed to still be sigma sub 1 squared over sigma 2 squared. Let me double check that. No, that's correct. All right. So anyway, to find this value on the table, and then we'll use R to find it a little quicker, or maybe finding a more exact value of it. To find the value of b, using the F distribution table, use table 7, and there's many pages for table 7, by the way. Table 7, we're going to go to row 5 in this case, and column 9. And what we're looking for is the F, the value of F, the F quantile that is in the 0.05, comma 5 degrees, comma 9 degrees, 5 numerator degrees of freedom and 9 denominator degrees of freedom in that table. So you'll sometimes see them write the degrees of freedom as a part of the subscript for these things in notations. So what we get when we do that, so go into the F distribution table, and we've got to go to, so you notice the denominator degrees of freedom, numerator degrees of freedom are up here. So we need to go to column 9 all the way over here, and then down to column 5. Yeah, numerator is 5, and then we have to go to 9. Sorry, so numerator degrees of freedom is 5. Denominator degrees of freedom are 9, but you don't see 9 here, so we need to go to the next page until we find denominator degrees of freedom 9. So go into column 5, row 9. We're right here. Oh, sorry. Right. I'm going to do that. We're right here in these values right here. So if you look right here, it tells you the different alpha values, and the alpha value we were looking for was 0.05 right here. And so if we come down to the 0.05 row in the denominator degrees of freedom 9 section, and come over to 5, we get 3.48. All right. And so we get that B equals 3.48. All right. So we got that from the table. Not too bad. It's not that hard. It's just have to be careful with what number you pull, because there's numbers all over the place. I would prefer to use R if it were me. So using R, we've got QF function that we're going to use, and we put in, instead of, we don't have to worry about putting 0.05, because we can do less than or equal to this value is 0.95, so we can actually put that in, and then 5 comma 9, and that should give us the same thing, but let's double check ourselves real fast. And so if I do QF and then do 0.95 comma 5 comma 9, hit enter, indeed I get 3.48. And voila, just like that, we've got our answer, and that's the value of B. So B does indeed equal 3.48. Okay, so not too shabby. So we went over a lot in the last 2 lectures. It's a lot to, none of it's terribly difficult, but there's a lot of information, right? So make sure you're really comfortable with it, because these are the things that you really want to be comfortable with from a statistician standpoint. Understanding these sampling distributions is important. So the recommended homework, which I'll go over in the next lecture, is section 7.2. Do 9A, 11, 12, 21, 25, and 31 in section 7.2's exercises. Some of the problems ask you use the textbook's applet. I don't know if we still have access to that or whatnot, but the applet's kind of a replacement for us using R or the calculator. So use R or the calculator to try to calculate some of those problems. I will show you how to get the answers in R specifically in the next video for the solutions, okay? Guys, I want to do one more quick thing. Hopefully it won't take too long, but it's an extension from example 7 we just did with the F distribution. I want to show you what you do when the variances are not equal. In that problem, the variances were equal, and I kind of skipped some steps in what you should do. So let's assume let's do that problem where the variances are not equal real quick. This is going to be important to you to know for one of the graded homework problems. So from example 7, we knew that N1, the sample N sub 1 was 6, N sub 2 was 10. So the degrees of freedom are 5 and 9 accordingly. All right. But what if the variances aren't equal? Say the population variance, specifically the population variances, say sigma sub 1 squared was equal to 3 times sigma sub 2 squared. Well, what does that imply to us? Well, that implies one of two things. It implies that the ratio sigma 1 squared over sigma 2 squared is equal to 3, or it implies that the ratio of sigma 2 squared, the reciprocal, over sigma sub 1 squared is equal to 1/3. Okay? Those are going to be important in us setting up to find the proper values. So in that one, I'm going to call it part A. The probability we found in example 7 was we were looking for s1 squared over s2 squared less than or equal to b, right? And that had to equal 0.95. All right, so what we were looking for there was an f value up here for 0.95 was below the value of b, whatever that f value was, and the value up here was 0.05. Okay. And so to correctly do this notation wise, to turn s1 squared over s2 squared into an f variable or into an f value, really I should call it an s statistic, f statistic, s1 squared. I need to multiply it by the reciprocal of this guy here. So sigma sub 2 squared over sigma sub 1 squared, that will turn that into an f. That must be less than or equal to b times 1/3. That's how we turned it into the proper f distribution here. And so if we clean that up a little bit, that's just saying what's the probability that of s1 squared over s2, I didn't want to write that again. That becomes an f distribution of 0.05, and I'll say why that is in a second. It mainly is because it's the alpha value up here, comma with 5 numerator degrees of freedom and 9 denominator degrees of freedom is supposed to be less than or equal to b over 3. And that equals 0.95. So we need to figure out what b over 3 has to be equal to here, either using r or the table. I'm going to use r. So if I use QF and I put in 0.95, because that's the area below in the image I drew, that's the area below here, and that's what the QF function finds. Finds the f value that for which 95% of the data falls below that, comma 5, comma 9. I get the same answer we got in exercise 7, or example 7, 3.48, I believe, yeah. So setting b over 3 equal to 3.48 and solving for b, we get that b equals 10.44. So a very different number because the ratios of the variances differ. So that's how you do that. But what if I wanted to find a different probability that was, instead of being less than or equal to some value, what if I wanted to find the probability that some value was less than or equal to the ratio of sample variances? So that is, find the probability that some value a is less than or equal to s1 squared over s2 squared. If we use r, we can do this exactly like I just did the other problem. And so r makes this a little bit easier. So, and I recommend you definitely go with that. So I'm going to multiply a times 1/3. I'm still going to use the same ratios up here to turn this into the proper f distribution. So I end up getting a over 3 is less than or equal to s1 squared over s2 squared times sigma 2 squared over sigma sub 1 squared, all right, which equals the probability that a over 3 is less than or equal to the f distribution of, instead of 0.05, it's 0.95 realistically, comma 5, comma 9. So the degrees of freedom stay the same for the numerator and denominator. And we want to know when that equals 0.95. Well, if we use the r function QF again here, we get that QF of instead of 9, since alpha is 0.95 here, we're going to plug in 0.05 here, comma 5, comma 9. And when the r will spit out for us the value of 0.21. All right. Now that's all nice and fine, because what we're finding here, and it should be a smaller value. Oh, undo that. It should be a smaller value here, but what we're looking for here is the area, something down here for the area is 0.05. It's probably closer to the edge than I'm drawing it, but 0.95 above. So the alpha actually equals 0.95, but we want the area to the left in the function. So that equals 0.21, and again we can take the a over 3 is supposed to be equivalent to 0.21. So solving for a, we get that a equals 0.63. And so if you use ours, this is a pretty quick procedure. The textbook wants you to use, in an example like this, and in the one I have in homework, I gave you the hint for doing it via the table. The table has some issues. The table doesn't give us alpha values as big as 0.95. They only give us alpha values of 0.1 and below. Excuse me. So you have to use a reciprocating trick to answer that. So I'm going to do the alternative answer for part B, and another way you can get the answer using the table. So if you want to use the table, here's how you do it. So still trying to find the probability that a is less than or equal to s1 squared over s2 squared. You got to use this reciprocating trick. All right. If you flip the ratio of variances in the a and change their sides, you got to reciprocate them to do that. So what I'm saying is it becomes probability of s2 squared over s1 squared, reciprocate that, less than or equal to 1 over a. Okay. Now we can commit to using the same trick we did in part A, because right now what we're looking for is the value up here where 0.95 falls below and 0.05. So what I've done is I've tricked the problem into becoming something I can look up on the table because it has an alpha value of 0.05. Okay. And so I do the same thing I did in the part A. I take s2 squared over s1 squared, but instead this time I'm going to multiply it by sigma sub 1 squared in the top, sigma sub 2 squared in the bottom. So the reciprocal of what I did in part A, less than or equal to 1 over a times 3. So that was that other version I saw here that I said there's an option, another option for it if you reciprocate things. And the reason why this trick works is because of the reciprocating factor. The value up here is often the reciprocal of the value over here. All right, it just happens to be the nature of how fractions work and ratios work. So this is just equal to the probability of f of 0.05, comma, now the degrees of freedom when we flipped the s1 and s2 squareds and reciprocated those, they changed too. So instead of being 5 and 9, it's going to be 9 numerator, 5 denominator. So those change sides, and that's going to be less than or equal to 3 over a, which equals 0.95. So once again, we're stuck looking at the table with 9 numerator degrees of freedom and 5 denominator degrees of freedom. And so from the table, we find that that value is, we go over to the 9 numerator, 5 denominator, come across to where they meet up, and then find the 0.05 column. See how it only has values 0.1 through and less and smaller? Then the value is 4.77, a very different value than we got, but that's okay. This is going to work out for us. So we get 4.77. We set that equal to 3 over a, and we will find out that a still equals, rounded to 2 decimal places, 0.63. All right, and you're kind of wondering, well, that value of 0.21 on the lower end makes sense, right? It does. If you take 0.63 and divide it by 3 straight up, you'll get 0.21. So actually, you can still get the value down here of 0.21. The value, and that would be 0.05 in the bottom. There's 0.9 in the middle. Now, this is kind of looking at the problem in a different way, not the answer to this particular thing. But in the upper part, we had the value. The F score was 3.48. So between 0.21 and 3.48, there's roughly 90% of the curve fits between those two values. And you could prove that in R, but we won't do that for now. So hopefully this will help you in the graded homework, and I just wanted to make sure you guys got to see some of this stuff. Again, use R, folks. It makes your life easier, and I don't have a problem with it. I just need to see the notation written out like I've got it here. Other than that, use R to get your answers. All right, guys, have a great one.